Hello everyone, I'm Saptarshi Mukherjee. I'm a software engineer 3 at Google. I have been a competent programmer. So in this playlist we are basically discussing the problems, the approaches and solutions for Codeforces round 923, which happened a few days back, I think around a week back, or maybe a bit lesser. And in this particular video I'll be discussing the problem F, that is microcycle. So I found this to be a very interesting problem. Before this, I have discussed some other problems like problem G, which involves very good application of DP. If you haven't watched, please go and watch those. And also, I've solved a few easier problems like A and D till now. So this problem stands very special because it is the only problem of graph theory in this playlist and in this contest, and it contains some pieces of graph theory which you can apply to many other problems. So there are some pieces that I've applied in this problem which I've applied in so many other problems before this in the last 2-3 years. Okay, so let's see what this problem is about. You are given an undirected weighted graph, n vertices, m edges, and at most there is one edge between each pair of vertices. So simple kind of a graph. Graph does not contain loops, so in every way it is simple, but graph is not necessarily connected. There's just a small thing you need to be very careful about. A cycle is called simple if it does not pass through same vertex twice and doesn't contain same edge twice. So a simple cycle graph is basically something like this. If we see this, 1, 2, 3, this is a cycle in a graph. It's a simple cycle. This cycle is going through each vertex exactly once and completing a loop kind of a thing. Now, we have to find a simple cycle in which the weight of the lightest edge is minimal. So we have to find such a cycle in this graph where the weight of the lightest edge is minimal. So for example, if I have a graph, which is like I have some cycle over here and then there are some edges, then I have a cycle over here. And if I have the edges like this is 3, 4, 5, and this is something like 2, 6, 1, 5. If these are the weights of these edges, these may be 7 and 2, or maybe 7 and 1. So I can say that this is my answer because this lies in this graph, this one, and this is the lightest wedge in the edge in its cycle. So this cycle here the lightest edge is 1, here the lightest edge is 3. So my preference is whichever has the smaller lightest edge or smallest lightest edge. So I will choose this one. My attention will be on this particular edge, and I have to return this cycle also, saying that this is the cycle where this lightest edge is there. Just so that we are clear, in this example, if you see, let's say we had 1, 2, and then 3, 4, 5, definitely we will not return this one because this is not an edge of a cycle. We will not consider this. But whatever cycles are there, whatever lightest edges are in that, so we will basically return this one. Our focus will be on the lightest edge in cycles. That is the question. Okay. Now, the question asks us to find such a simple cycle. Lightest edge should be minimal, and what do we have to return? We have to return the minimum weight of the edge that we have found. Then we have to return the number of vertices in that cycle, and then the vertices of that cycle. So these are the k is the number of vertices. We have to first print that, and then k integers, saying that these are the vertices of the cycle in traversal order. So in any order, basically. Over here, I can say it is 1, 2, 3, or I can say it is 3, 2, 1, something like this. So in any way you're traversing the cycle, so you have to basically say the vertex numbers there. Okay. So now the question is how to solve it. As I mentioned before, first we should understand from the test cases. You can verify from the test cases. It's basically the same as I have shown over here. You can see that how it is, you can understand it better from the given test cases. But I hope you have understood the problem. Next thing is look at the constraints and try to figure out. So in the graph, usually the constraints follow one or two of the usual patterns. Here we can see that number of nodes and number of edges both can go up to 2 into 10 to the power 5, which means n square is not possible. Maximum n log n or m log n, that kind of thing is possible. M into log n or m into log m, whatever. Okay. And nothing more special over here. There's a very common kind of a constraints set in graph questions. Now the entire attention of mine is how to solve it. So we have to find a cycle edge of minimum length. Simple. In the whole graph, cycle edge having the weight. Minimum weight. Now, how to find that? Cycle edge of the minimum weight. One approach that immediately comes to my mind is, hey, if I have the list of all the cycle edges, then I know the weights already, so I can pick out the one with the smallest weight. So the question has two parts. One is cycle edge with the lightest weight. Now, lightest weight part is very easy. I know how to find the lightest weight. But if I know if it is a cycle edge or not, it is very easy to find. So I basically, this is my strategy that, okay, I have to find two things. One is a cycle edge. Another is that lightest. So whether it is lightest or not, it's easy to find. So if somebody can give me the list of cycle edges, then it shall become easier for me. How to find this? How to find this list of cycle edges? This actually is a very standard problem. I had taught it around 2 or 2.5 years back. I'll cover it in very short in today's session in a 10 minutes kind of manner. So to find a list of cycle edges or list of edges in cycle, we can find out the opposite thing, that is the list of all edges minus the list of bridges. Now what are bridges? Bridges basically are, for example, this line, this edge. If I delete this edge, I am dividing the graph into two different connected components. So this earlier was one connected component. Now the moment I remove this bridge, it is becoming two different connected components. So such edges are known as bridges. And if you think a bit, cycle edges are those. If you remove one edge of a cycle, the cycle doesn't care. The cycle, still the edges are connected, still the nodes are connected. So over here, if you remove one edge, still this 2, 3, this entire thing is connected. So in a graph, on removing an edge, if no two parts of that connected component become disconnected, then it is not a bridge. So cycle edges are not bridges. So basically I'm saying that find out those edges which are not cycle edges. How can I find it out? How can I find out those edges which which can break the graph into two different disconnected components? Like if I remove one edge, it will be it will lead to more components than there is currently. Now there is a standard way of finding this. This can be found out through a very standard algorithm known as Tarjan's algorithm. So this is one way. If it gives me the list of bridges, I can say that the remaining edges which are not bridges are basically the list of edges in cycle. And among those edges, the moment I have that list, the moment I have this list, I will get that list. The moment I have this list, I can find out the lightest by simple comparison of the weights. Just take the minimum weight. That's it. Now how to use Tarjan's algorithm? Let me show you using this quick example. So we can start anywhere. We can start a DFS kind of thing anywhere over here. Let's say we start from here. This is our starting point. So there are two things I will maintain. One is when are we entering in, and another thing is basically a low variable. So I'll discuss this low variable. First of all, I'll say that okay, we are starting over here. So now the timer is 1. I am starting over here. Low is 1. Next, or let's start at 1 maybe. That might make the example more interesting. Let's start at 1. I can say okay, I'm starting over here. So n is equal to 1 and low till now is equal to 1. Next, I'll move on to the next one. Let's say I'm moving to 2. I'm doing a DFS, so I can move to 2 also, 3 also. If I move to 2, I'll complete everything in 2. If I move to 3, I'll complete everything in something like that. Yeah. Now, when I go over here, my in is basically 2 and my low till now is also 2. Then I can go anywhere. From 2, I can go to 3 or I can move to 4. Let me move to 4. When I go to 4, my in basically is 3. That is the timer. So basically I'm maintaining a timer. uh, this is a very popular popular technique in graph questions. While you're doing a traversal, maintain a timer. So keep on increasing the count. In is my timer, that when I'm going in that node for the first time. Then low till now basically is the same thing. Now I'm going back. When I'm going back, I know this is my parent. I'm basically leaving my node. So nothing special over here. From 2 to 5 once again I'm going. My in becomes 4. Low is also 4. Now I'm going back. From 2 I know there is another place to go. From 2 other edges are visited. Now this is the last edge. So I'm coming here and I'm saying that in is equal to 5. Basically in I'm incrementing gradually. So it's a timer that is going on. You'll see the code, you'll understand. It's a simple thing. Then the low till now again is 5. Low till now, whatever I am doing is very clear. Low is equal to in. So low stores something. It's supposed to store something, but for now, low is equal to the entry time. Now from 3, I will try to go to 1. I haven't visited this edge. This 1 is not the parent of 3. So yes, this is a new kind of a node, at least for this guy 3. But what 3 will notice is that this has already been visited. This has already been visited. So this is not the parent of 3, but an ancestor of 3. But an ancestor of 3. What am I saying? Basically, when I'm going to 1 from 3, I know that, okay, I have come from 1 because 1 has already been visited. And 1 is not my parent. We know that parent of 3 is 2. That means there is a different thing, different way I came through 2 up to 3. I did not come from 1 directly, I came from a different route. So this green and this yellow lines are different. This yellow line and this green lines are different. Why? Because the parent of 3 is not 1. That means there is a different parent of 3 which is lying over here. The moment we know that this green and yellow lines are different, what do we know? They together form a cyclic path for me. Correct or not? This green and yellow lines form a cyclic path for me. So basically, when I am at some edge u, I'm going to go to v, and I know that, okay, v has been visited already. If v has been visited already, that means, and it is not my parent, that means I had started from v, or I was going through v, then through a different route I have come to u. And now from here there exists a single edge over there, which means if I combine them together, that path and this edge, then I get a complete cycle. And this is that complete cycle for me. The moment I have this complete cycle, I know that, yeah, there exists a cycle. This edge, which connects to an ancestor, which is not the parent, it connects to an ancestor which is not the parent. If it is a parent, then it's the basic edge. Like this edge also connects this to its parent. We cannot count it. This is not a cycle thing. But if we know that 3 is getting connected to some ancestor who is not the parent is different in the DFS thing. Parent means according to the DFS traversal, from whoever we came, that is our parent. So if there is such an edge which connects us to an ancestor who is not the parent, we call that a back edge. This is a back edge. The others, you can call them something like, so this is basically our back edge, and others are normal edges, or sometimes we refer them as tree edges. Tree edges. Why tree edges? Because you are basically moving, before you detect a cycle, you are moving through that edge to discover new nodes. That's when it behaves like a tree. When you're trying to go back to a visited node already, that is like you are going back. So it's a back edge. So that's it. If I notice a back edge, that means there is a cycle. And how can I now mark it? I can basically say, okay, now your low, adjust this low to be the entry point of the node you're going to go to. So in equal to 1, this is where we'll update this low to 1. Right? When I'm going back, from 3 to 2, going back means from 2 I had called DFS of 3, from 2 I had called, from here I had basically called DFS of 3. Now when it will come back, when the control will come back, then I'll basically do this kind of a checking that, okay, for 2, low 2 initially was 2, but low 3 is 1. Low 3 is 1. That means 3 actually has reached a component or reached some part of the graph which was first entered at 1. According to this DFS traversal, it was first entered at 1, which means this 2 also belongs to that particular cycle or that particular part of the graph. This 2 will also say, hey, if you basically found access to a back edge, I am also part of that. The edge from me to you is also part of that cycle which you are a part of. If you got an access to an ancestor, I also have the access to an ancestor. So this will basically say, okay, my law is also going to be the same thing. The law of 2 will change to the law of 3 and convert itself to 1. What does this law help in detecting? So if an edge, when you're going from a certain node U to V, when you have come back from the V and you have uh, configured all the low and all these things, if your this is your entry time and this is the low, if the low is greater than this entry time, that means it is a bridge. So we are moving from U to V during a DFS. If after all this traversal, all these computations, if we say V still has a low value greater than IN, that means V has tried all the packages, but still V was not visited before you. V cannot be visited before you, or no part of V was visited before you, which means that V is not part of a cycle which contains you, by which they could have become equal. If IN becomes equal to low or becomes greater than equal to low, basically, then we could have said a different story. We could have said, okay, they are not bridges. One way we can quickly start with a different node, let's say 1, and then we can say this is 2, 3, 4. We can go something like this. Let's say TIN. So IN is equal to 1, low equals to 1. Over here we are visiting first, so IN equals to 2, low equals to 2. Then we are visiting here IN equals to 3, low equals to 3. Then we are visiting here IN equals to 4, low equals to 4. Now when we are visiting back over here, this is a back edge. This is a back edge. So we will update it with this with this entry point. We will say, okay, this will become 2. And then similarly this also becomes 2. Why? Because we are basically saying, okay, from I am going to from me I'm going to you. You are a part of a cycle, so basically we'll be part of the same cycle. So this is 2, and so this one also changes itself to 2. When I'm going back, similar thing happens, but already low is equal to 2, so no changes. This guy, it asks that, hey, your low is 2, your low is 2, but my low is better. Your entry point is okay, so its entry point is better, so definitely uh, wait a minute, this guy sends it to DFS. This guy says that the low value currently is 2. Yeah, that is fine. So this low is equal to 1, so it is already at a better low. This will not change itself. So what are we finding out? That this is a part of a cycle. How? Because this IN value is greater than equal to this low value. Is it greater than equal or less than equal? If it is less, that means it is a bridge. So it is greater than equal. That means it is not a bridge. This is a cycle. This IN value is greater than equal to this one. Yeah. So if IN of the parent is greater than equal to, or IN of U is greater than equal to the low value of V, then we say that UV is a part of a cycle. Is a part of a cycle. You can see over here it is so. Similarly over here, IN4 is greater than equal to low over there. So this is also part of the cycle. Now over here let us see IN1 is not greater than equal to 2. So this is not a part of the cycle. This guy is independent because this was visited before any of the next things have been visited. Any of two or its cycle has been visited. So we understand that one is outside that cycle. This is the test. So we are basically comparing this IN with the low values of the upcoming descendants, you may call. That's it. So this is Tarjan's algorithm in very short. You can apply this algorithm and you can solve the given problem. Um Okay, so this is how you can form the list of bridges. So what I did was I formed the list of bridges. From there, what did I get? I got the remaining edges, the list of cycle edges. And from there, what I did? I figured out what is the minimum weight cycle edge. Cycle edge. Let's call that as UV. When I found UV, now I have to find a cycle. I have to find a cycle for U and V. What I did for that, you can see the code. It's a you can do in multiple ways. I used a BFS technique. Why? Because if let's say U and V are 5 edges apart, then BFS will basically go by breadth. So in 5 iterations of that BFS, where it basically pastes everything in 5 levels of BFS traversal, you can say, we will get back from V to U or U to V, however. So we go in this way that okay, we know U and V. Now basically start from V, let's say. Start from V, or you can start from U also. From V, don't go to U. Go to every other edges, every other nodes. Take them, store them in a queue kind of a structure. And then from each of them, keep on going, keep on going. It's a level order kind of traversal. From one of them, at one point you will see, you will get back to U. We won't go through long paths which would have happened in DFS. So for this part, if I have to get the cycle from this, find cycle containing the edge UV, I basically use this. I start from either U or V. In the next level of that traversal, of BFS traversal, I don't take the other one. If I start from V, I don't take U in the next one. I'll take all the other vertices. From there, I'll go in multiple levels. In the second level or third level or fourth level, I will eventually end up at U. So it's a very standard BFS technique. You can see the my code and you can use it in many popular BFS questions. Okay, so let us see. Let us take a quick look at the code. Yeah. Okay. Um, this part is redundant, it seems. Int uv 298. Okay, sorry, I'm looking at the same solution. Sorry, I'll open this solution. I've, okay, yeah. So solve function. Yeah, what I did over here is I basically took this visited tin is the entry point in, and this is the low. I passed them. I did a DFS over there to find out all the bridges. This is that function where I'm doing that thing. So this is the initial thing. This is a timer. It started as a static variable. I started it with 1 over here. Timer equal to 1. I think I did somewhere. Timer equal to 1. So now what am I doing? I'm basically saying that okay, when you are visiting some vertex for the first time, you have a certain counter in both your low and tin. If then visit all your next vertices. Don't visit your parent once again, because we know that there is an edge to parent, but we should not visit it. That's the same edge where we came from. We should not repeat edges. Then viz of x, this is something. So that means if x is visited, if x is already visited, that means this is a back edge. So that means this is the condition of the back edge. Whenever I'm going to a back edge, I'll say okay, I'm a part of your cycle. So I will take the entry point of x in myself that okay, this is the lowest thing I have for myself now. And in other case, it's a tree edge, so it's a new edge. I'll go to that. It's a DFS recursive call, and then I'll say okay, now my low is basically the low of that X. I'll update it if it can be updated. So and then now I'll check. This check can happen before the assignment as well, before the previous assignment. That if my entry point is lesser than the low of X, then add this. Then add this. I could have done the other thing also. Over here, I could have replaced it with the opposite sign, and I could have said these are the cycle edges. That directly would have solved my problem. But Tarjan's algorithm was written first of all keeping bridges in mind, so I've preserved that thing. You can do it the other way as well. So this is my bridge. I've showed this already in the example by drawing over there. So yeah, now when I'm going back, I have the list of bridges, and now I'll visit the edges in the increasing order of weight. I've sorted these edges in the increasing order of weight over here using comparator sort. You can take a look at my code. You can already see the link, etc. So over here, I have the first time I see that it is not a bridge. First time I see, so I'm going in the increasing order of weight. The lightest edge that is not a bridge is my answer, or is an important part of my answer. So that is where I break, and I take it in last. As a matter of convenience, just some variable last. And now these are my two vertices U and V that form that edge. And now I'm doing the BFS that I mentioned to find out a cycle containing the edge UV. This is that BFS. So parent and visited and something over here. Basically, I'm doing a simple BFS over here. You can take a look at this later. It's a simple BFS. You have many problems on BFS actually using this. So you can use your own algorithms as well. Finally, yeah. So up to here is my BFS. When I found the V, I started from U, I think. When I found the V, then I'm stopping. And then I'm basically tracing the path. How? I'm storing the parent. At every level, I'm basically storing the parent where I came from. So over here, I'll store, let's say uh, at this node, I'll be storing here V is my parent. At this node, I'll be storing, let's say this is X. So I'll be storing that X is my parent in this way. So parent equals to V, parent equals to X, and so on. So this is Y. In the next one, I'll store that, okay, my parent is basically Y. This may be something like Z. And in this way. So in this way, when I start again from U, I can go, keep on going back because my parents are stored. For each element, my parent is stored. You can take a look over here. Parent of V. So I'm basically going to parent of V at every step. At the final stage, you have to keep some base case where you started from. So when you go back to U, you have to, or when you go back to V, you have to say that, okay, that is where you started from over here. When you go back to the initial place where you started from, you have to keep something over there as the parent by which you can detect that this is where I started from. So most of the times I keep P is equal to V. That is same thing. In this code, I have started from U and completed at V. So you'll get just the converse things, but logic remains the same. I'm printing the length of the cycle here, and then, here I'm printing the length of the cycle, and here I'm printing the nodes of the cycle. A plus 1 because I had initially taken this in the zero indexed form, all the vertices. So at the end, I'm doing a plus 1 so that it comes back in the one indexed form. This is one solution. There is another solution as well to this problem. This solution I have actually explained based on some very well-known algorithm, Tarjan's algorithm, but not everyone knows Tarjan's algorithm, or not everyone is always confident about using it, or can actually implement it totally correctly till the end. There can be confusions, etc. A lot of things can happen. So often we have to keep other measures. So you should learn Tarjan's algorithm so that you can use it somewhere where it is definitely the best choice. Over here, it is not that important. You can solve this without Tarjan's algorithm as well. If you have to solve this problem without Tarjan's algorithm, then you have to use some kind of greedy approaches. For example, we need only the lightest edge. We don't need all the edges. We don't need all bridges. We need only the lightest bridge. We need only the lightest cycle edge. Lightest edge which is not a bridge. So, if you think how we can basically form it, one way is that cycle edge and bridges. The main difference is that cycle edge connect two parts that are already connected. So if I consider this kind of a graph once again, what is the difference between these two edges and these three edges? The pink edges are such, if I remove the pink edge, they are not disconnected. So when I add the pink edge, let's say all others were connected already, and I add this pink edge at the end, all other edges are there. This does not do any new thing. This connects two vertices which were already connected by different path. So these were already connected through a different path. I'm just reconnecting them. But bridges will actually connect to new parts of the graph. So how can I detect a cycle edge? That okay, if it is connecting two things which are already connected. Now, if I start connecting, if they are not there, if I start connecting, let's say that okay, I will consider each edge one by one. When I start connecting, I can say, hey, when I start connecting these two, initially let's say they were not connected. I have removed all the edges and now I'm trying to see whether they are connected or not. So I can say, okay, when I'm connecting this, this may seem like a bridge. Eventually this is not a bridge, but now it may seem like a bridge when nothing is connected. When I'm connecting this, then maybe I'll say this is also a bridge. And when I'm connecting this, then I'll say, okay, this is a cycle edge. This is a cycle edge. I know this. But the reality is that these two were also cycle edges. So the anticipation might not be correct over here. But what we know is that only the lightest cycle edge matters. Lightest cycle edge matters. So if I say consider edges in decreasing order of weight, let's say you had something like this 5, 4, 3, 1, 2. If I say let's consider edges in the decreasing order of weight. So first I'll consider 5. I'll say okay, 5 is connecting. It is not necessarily a bridge. We don't know if it is a bridge or a cycle. Now it appears like a bridge. We don't know. Then comes 4. I know okay, this also can be a bridge, can be a cycle, depending on what comes next. Now the next edge weight is 3. When I'm connecting this, I'm damn sure that I'm connecting two connected parts of the graph. Or a connected part of a graph, I'm reconnecting it. I'm damn sure this is a cycle. So if I go in the decreasing order of weights, edge weights, what is my guarantee? This guarantees that the lightest edge weight, the lightest weight edge will be visited last in a cycle, will be visited last in any cycle, which means if I visit in the decreasing order of edge weights, think about any cycle. If there is a lightest wedge, I'll visit that at the last. All others I would have visited. So when I add that lightest edge, all other edges are there. This will complete a cycle. I'll be able to understand that this is connecting already connected pieces of the graph. That's it. So I'm guaranteed to find remaining part of the cycle is already connected. Which means I can easily detect that it is a cycle edge. We can detect that as a cycle edge immediately. We can immediately detect that as cycle edge. So that's the strategy you can use to solve this problem without knowing fancy algorithms. There was a point of time when I did not use any fancy algorithm at all. When I became a master at Codeforces, I knew very less, fancy algorithms to say. Segment trees, Fenwick trees, I'd used very rarely. In one or two problems, maybe in some contest, I'd used that. For this one, you need some way to know that an edge is connecting connected pieces or disconnected pieces. There is a very popular algorithm for this. to find out whether connected or disconnected, that when some edge is basically joining u and v, whether they are connected or disconnected already, whether they are connected or not, can be found out using DSU, disjoint set union. Some point later maybe I can take some elaborate session on this. Over here this is slightly beyond the scope of this session to discuss the details of DSU. You can use my template. You can basically I can explain a bit when I show the implementation. This helps you to actually keep considering edges, keep on adding edges, by which you can connect different pieces of the graph, and that helps internally maintain some internal root by which all the different nodes of a single component are recognized. So there is a representative of every connected component. And when we join two components using some edge maybe, then one of the roots becomes the new root of the entire component. And that root is chosen based on some optimization techniques. We say that the component which is greater in size or which has the greater height should be made the new root, because the other one can simply become a part of that entire tree. So that is how it is. If I remember correctly, it will not be a binary tree. It will be a multiple, one basically root will have multiple children, can have multiple children. It's a very interesting technique. There is a lot to understand here, but for the time you can also use my template and you can use this. So this is a simple technique which occurs in many simple computer programming problems, as well as your interview preparation kind of problems. You can use it, and over here basically keep on adding edges in the decreasing order of edge weights. Every lightest edge of every cycle, every or the lightest edge, lightest weight edge of every cycle will definitely get recognized as a cycle edge in this algorithm. So definitely keep on taking the minimum. You can say that while you're going in the decreasing order, whichever is the last edge which you find is a cycle edge which joins two already connected parts, that will be your answer. So if you're over here, you will join in this way: 5 4 3 2 1. 5 will say that hey, I am a bridge. Till now it is connected to different components. 4 will say I am a bridge. 3 will say I am a cycle edge. 2 will say I am a bridge till now, and 1 will say I am a bridge till now. So what will we say? We will say, okay, from the last, if we see, 3 is the first guy who is a part of a cycle. You can have complicated cycles as well. This algorithm will definitely work, because below that last cycle edge, whatever else are there, they are definitely bridges. These will definitely be bridges. Your algorithm cannot say which exactly are bridges. From the beginning, it cannot say which are bridges, which are edges. This algorithm is not suited for finding all the bridges or all the cycle edges. You can't find that. But for this problem, that is not necessary. For this problem, you don't need to know all the cycle edges or all the bridges. And that's the reason I mentioned this later on, that okay, if you have to solve this in an easy way, you have to be very focused on those simple words, those important words. Lightest. Why lightest? What can I exploit using that? So over here, we did not have to use the Tarjan's algorithm because of that word lightest. So I have shown two different approaches. Let's quickly look at this code. This is the previous one. Okay, this one. So what I have done, this time I have sorted based on the decreasing order of edge weights. You can look at my pair implementation. There's a comparator function which I discussed in a few sessions before this. So it's p dot c minus c. You can see over here, this is my condition. That means according to c, whichever is greater will come first. This is the basic meaning of this. Okay, now let us see what am I doing then. This parent rank is my DSU thing. I am initializing it first. Initially this make set, if you see, make set basically will make v as the parent of v, and the size of this component is 1. So initially each vertex is a single component containing only that vertex. Then I am saying that okay, now keep on joining the edges. What will I say? That okay, find the set for both the vertices of that edge, and if they are different sets, then union them. So I'll say if they are different sets, if they are belonging to different sets, then union them. Union sets is written in this way. Show a quick look. So as long as you're not finding a common root, you will keep on going to the parent, something like that. So based on the rank, you will go to the parent. There is this algorithm, and then finally you will say that, okay, um, parent of B is equal to A. Okay, so we are finding the root of A and the root of B, and then we are checking if the roots are different, then join one root to the other root. Okay. So you can look at it in detail. I can also maybe take a separate session on this later on, but for now, this is what it is. So join the root of one representative to the other root based on what their ranks are. If A's rank is lesser, then join A to B, something like, join A to B, otherwise join B to A, something like that. And then a rank, basically here I'm storing the size of that component in the rank. Okay. Next, yeah, and in the else part, if they are in the same component, that means this is a cycle edge. So if they're in different components, join them, and if they are in the same component, then mark that as the last. So I'll keep the loop going on till the end. Whatever is the last cycle edge, that will come over here, and using that I'll do the same BFS thing that I did in the previous solution. That do a BFS from one vertex to the other vertex. Don't take the other vertex directly in the first iteration. Later on when it will come, you have a complete cycle. To get back the cycle, you need to store the parents at every step, parent in this BFS traversal, and from there you can derive the entire cycle. That's it. This was a slightly long session, but I hope this was worth it. So there were 2-3 different techniques I hope you got to learn through this session. If you find the videos informative, do let me know. Do like, share, subscribe, and share with folks who might find this video informative. There's a lot of effort that goes in these videos to plan and also present in a way that it can be comprehended easily, can be understood easily. So thanks for all the support till now. Looking forward to the same in the coming videos. I hope you all keep coding in the coming contests and then come back and see the editorials how I'm solving the problems. So yeah, take care, keep coding. See you all in the next videos. Goodbye.